section 6.1. Chapter 6 in general is we talk about the analysis of structures, and in section 6.1 we're going to talk about trusses. I have the PowerPoints loaded up to our Moodle page, and as far as this file goes, let me put this up here, the file, the PowerPoints for chapter 6. Today we're going to cover slides 1 through 12, but we're skipping number 10. So in general, we are not going to talk about space trusses at all. In section 6.1, we're just going to cover subsections A and B, and we'll leave C and D for later. But one of the main reasons that we talk about trusses in statics is, the good news for you is that we're back into two-dimensional stuff. We're going to stay two-dimensional. And the other reason that we talk about it, the big application is this is a good introduction into mechanics of materials, which is a course that you will be taking following this course, either by 1 semester or 2 semesters. But mechanics of materials starts looking at the internal loading, or the internal response of different structural members to external loading, and that's what's going to happen here. So if we come back over here and take a look at some of these PowerPoints, we'll go through this and then I will work a problem using something called the method of joints. There are two methods that we'll learn in chapter 6. One is the method of joints, one is the method of sections, and they both serve to analyze trusses, but they both do exactly the same thing, but just depending on the truss and what you need to find out about the truss, one or the other will be less difficult and therefore more applicable. So first of all, what are we talking about when we discuss the idea of a truss? Well, the structure shown on this slide is not a truss. This is actually a type of a frame. But basically, we are looking at the internal responses. So for example, if we have this frame where we have a hinge here at C, and we have some sort of a supporting arm from B to E, and we have a weight here at F, and we have a guy wire from D to G, what we're basically doing is trying to distribute this load of the weight W so that it's borne on different parts of this structural member. And the way that we analyze something like this is by looking at everything that's happening on the structure, for example, the tension from D to G, the weight, and the reactive forces at A as being external, and then analyzing based on that. Now, there are 3 different things that we'll talk about: trusses, frames, and machines. Frames contain at least one multi-force member. In other words, something acted on by 3 or more forces. A truss is formed only by 2 force members, straight members with endpoint connections, and machines are structures that contain moving parts. So our discussion of chapter 6 is going to focus on frames and trusses. Now, a truss, this is an example of a very simple part of a truss called a rigid truss. A truss consists of straight members connected at joints. No member is continuous through a joint. So if you look at something like this, truss A, B, C, D, you have connectors where A, C joins AD, that's point A, D connects AD and BD, but this member on the bottom is not continuous. In other words, it's broken here at D, and we could have different reactions on one side than the other. In this case, we're not going to, I can see already. But that's, a truss is generally built on a triangle as well. It's not, I don't know if it's 100% true or not, but generally triangle shape indicates that you have a starting part of a truss, of a rigid truss or a simple truss. All right, most structures are made of several trusses joined together to form a space framework. So like if you look at bridges, for example, they will often be a series of different trusses. As a matter of fact, I'm going to come over here to a different class that I teach, Mechanics of Materials. I'm going to see if I can show you. All right, this is a bridge that is made up of trusses, and the reason for that is if you think about it, this is a nice old bridge. It's made out of wood. As cars or vehicles drive across this span of the bridge, there's going to be a big load placed where the car or the vehicle is. And so the other pieces of the structure are designed so that that load is distributed, or in other words, so that the load of the car doesn't bow the center span of the bridge down, for example, and the load is actually borne by the other members of the structure. Now, a lot of structures are very symmetrical like this, where there are two triangles, for example, here, two triangles here, but they're directly behind each other and they have the same measurements, so that the weight is borne. If the load is in the middle, the weight will be borne in a symmetric fashion within that truss. But that's sort of an example of what a truss looks like. There are more complicated trusses, such as the here in the background, the Mackinac Bridge, which is connects the lower peninsula of Michigan to the upper peninsula of Michigan. You can see that here this bridge is greatly bowed upward, which is a design feature. There are pillars that have suspension cables, and the bridge is suspended. The span of the bridge is suspended from those cables. And the Mackinac Bridge is actually the longest suspension bridge, I believe, in the United States. Then there's one other, a little closer to home. I don't think I have a whole picture of this. Here it is. There it is. The Willwood Dam Bridge. Isn't that beautiful?
Yes.
Yeah, so the Willwood, now the roadbed is over here, off to the lower left-hand corner of this picture. But this used to be the main artery that went between one side of Willwood and the other. But basically, there's a dam underneath it, and then, as you see, everything's built on triangles, and those triangles are built to support. They are usually built on triangles, absolutely.
In Turkmenistan, we also have a lot of triangle bridges.
You do? Yes.
So under above the big flow of water.
Yes.
Or the railroad.
Yes.
It keeps stable.
It does.
I think it's trusses.
Uh-huh. Yep, absolutely right. Very, very good.
But
good connection.
So I got that. What was the example on the slide?
Yeah.
The point is not connected, right?
The which?
There was on the slide.
This
on
one?
The presentation. No,
Oh.
the presentation.
Yeah.
So then on the presentation for chapter 6, it's going to be that the trusses will be the lower points at a deep point. That's
Yes.
going to have the power. That's going to be the most force applied there.
Exactly. That's exactly correct. So, and then we analyze how that load, P, is distributed in the different structural members. So, in terms of just the definition, the pieces that are connected, for example, element AC, element C, B, and so forth, are referred to as structural members, and they are connected at joints. Okay, so like B is a joint, D is a joint, E is a joint. This is kind of the big thing. When we're used to thinking about forces being positive to the right or positive upward in the y direction, in a truss it's a little bit different, or in any structural member. Every structural member is either going to be in tension, which means it's being pulled on, or in compression, which means it's being pushed on, or it's going to be neutral. But the force on one side of the structural element and the other are going to have to be equal and opposite to each other. And whether the pulling indicates tension, the pushing, so this would be a member in tension, this would be a member in compression.
Okay.
But the magnitude has to be the same, or else the structural member would move, which is, yeah.
Would tension and compression be then the same number, the same numeric value, but they're going to be different signs?
That's exactly correct. Yeah, tension is normally considered to be positive, and compression is considered to be negative.
Why though?
Yep.
Like usually, like in calc, for example,
Yes.
we had some examples like, but it's not related to this, but like if they will come at the same time perpendicular to one positive, but why is it different?
I see. Right. This is a little bit different because we're thinking about what the structural element is bearing. So if you're pulling on it, it's tension, and if you're pushing on it, it's compression.
Oh, okay.
So, and what's pushing or pulling on it would be the joints,
Okay.
right? Yeah, very good question. Excellent. So this is sort of a different view of a truss, and as it says, most of them are in space. They're not really two-dimensional, but we are going to restrict our conversation to just two-dimensional trusses. And here are some examples of trusses, and just to bring home that point, they are all built on triangles, aren't they? If you look at that. So the kind of trusses that we looked at for the bridge, they tended to be Warren trusses, right? Where they're just sort of like M's all the way through. So if we take a look at that, there you go. You see how that's just a perfect little chevron shape. Yep. So Warren truss. But Warren, Howe, and Pratt trusses, as well as this, which is called a Baltimore truss or a K truss, are all bridge trusses.
Would then Warren be more symmetrical?
Well, there's more degrees of symmetry, absolutely, because these are symmetrical about in some ways, but the degree of symmetry in a Warren is quite high. The roof.
What does the shape of the truss depend on? Like, for example,
right.
Cove and Warren. Does it depend on the conditions?
Right.
Geological?
Well, mostly I think it depends on the building materials, because we don't really get into and that's a great question. But depending on how much load you have to bear and how the load is distributed, you need to choose building materials for that fitness of purpose.
Oh, okay.
And so you may or may not have what like you can't build a bridge out of like titanium or whatever. If you've got a long span to cover, you're going to choose a truss based on that sort of a span and what materials you have to use. Pratt, Howe, and Fink, the ones on the top, are roof trusses. And so and they have another truss they don't have here. It's a little bit more difficult to analyze, but it's called a scissors truss. And what a scissors truss does is it allows the builder to open up the ceiling a little bit so that you have like a cathedral ceiling. I'm going to draw a picture of sort of one here. But like if you see a scissor truss, they sort of are like this. And so you try to keep, and there's always like a big heavy plate that connects it right here. But they want to keep this space open so that you can keep your roof line open to keep a nice big architectural feature.
Okay.
Yeah, good questions. All right. So a rigid truss, we start about this type of a triangle. You notice if you push on A, B, or C, that truss is not going to compress. But if you have something that's built more on this trapezoid, if you push on B, it's going to splay C out from its original location, and it'll actually collapse. So this is a non-rigid truss, whereas this is a rigid truss. And then a simple truss is built on a rigid truss, that basic triangular truss. Now, if you look at a truss like this, which is a square all the way around, and this kind of answers the question that you were talking about earlier, we start building on triangles, and then at some point part of the feature may not be a triangle, but if it's still rigid, in other words, if pushing on G won't tend to splay A outward, which in this case it won't, it can still be a rigid truss. But the foundational piece of that truss is definitely the triangle.
Okay.
Yeah, you ask good questions. I appreciate that. All right, so when we talk about the analysis of the truss, what we're saying is that if you look at a truss like this, every one of these structural elements, AC, CD, CB, DB, and DA, are all going to have forces acting on them, and that the forces are all going to be directed along the structural members. So, in other words, if we look at what's going on here at C, we're going to have a force directed either pushing or pulling on C from this joint, pushing or pulling on C from this joint, from this structural member, pushing or pulling from this structural member, pushing or pulling from this structural member. So when we know the geometry of this truss, we also know the geometry of the forces involved. And because it's sitting still, we also know that the summation of forces into each one of those joints has to be zero.
Zero.
Exactly, because if it isn't, then we're going to have something that's going to move or break, which is not what we want to do with the truss, right? So, so what we talk about here, we're not really going to discuss this. We talk about special loading conditions, but in our discussion, we're really going to limit that to 2 force trusses, and we're not going to talk about space trusses. So here in slide 11, we're going to start with a process called the method of joints.
You have the same actual
We do, and I'm actually going to just leave this problem. I'm going to work a different problem for you out of your homework so you can see how it is. But the purpose of our analysis in this section is to determine what the force is in each one of those structural members. So here, what you'll see is the first thing that you always do when you're analyzing a truss is you do statics. So you take the external forces and you find the reactions. So for example, if you look here, point C is a connected point and point E is a connected point. So you know that there's going to be reactions at C and reactions at E. So the first thing you do is you call those out as forces, and then you do the summation of forces in the x direction, summation forces of the y direction, and you can also do summation about any point in order to have a third equation to find those other reactions. Then what we do is we start at any joint and we think about each one of these members as either pushing or pulling on the joint to find out what the magnitude of the force is in each of those structural members, and then we can decide if it's in tension or compression. So before I work this problem, I want to show you that, for example, the force in AB we've determined, which I'll show you how to do in just a moment, is 1,500 pounds, and we say it is in tension. What that means is, if we look here at AB, that means that the force in AB is not pushing on the joint, but rather is pulling. It's pulling toward itself. So the whole thing is the direction of the force in AB will be one way on one side. In other words, we'll be pulling this way and pulling this way. It looks like it switches if you think about it from analyzing it, because it has to actually be zero, just whether it's bearing tension or compression. But the sum over the course of that has to be zero. So if it's like a positive 1,000 on one side, it's going to be a negative 1,000 on the other side. But we define it by being tension or compression. And doing that, we can work through an entire truss and determine what the forces are in each of those structural members. All right, now to illuminate that, what I'm going to do is to work a problem from your textbook for you so that you'll have this in your notes. And I'm going to start here with problem 645, and it says determine the force in members BD, which is right here, and CD of this truss shown. All right, so I'm going to go ahead and draw this to begin with. This is problem 645. And I have a connector here at A, and I have a connector here at H, and I have, my truss is comprised, this is kind of a Howe truss, isn't it? This is C and E and G. C goes to joint B, and E goes to point D, where there's an applied load of 36 kips. Kip is a kilopound. And from G to F, we have an applied load of 36 kilopounds as well. Kilo meaning thousands, so it's thousands of pounds. C, E, G, B, D, A. So I'm going to have a reaction at A in the y direction and a reaction at A in the x direction. Now, if you look here at point H, point A is a rigid connection. This looks like it has little rollers under it, which means that it will slide this way. So that means that H will only bear a load in the y direction. If it rolls in the x direction, there's not going to be any load that's borne there in the x direction. So I would just draw it like this, the reaction at H in the y direction, because the reaction at H in the x direction is 0. And they want us to find the force in member BD and member, oh, I didn't finish drawing my truss. That's not very clever of me, is it? There we go. There we go. And in member CD, right here. All right, I'm going to widen this out a little bit so we can see the whole thing. There we go. All right, so the first thing that we need to do is to do our static analysis of the outside part of the truss. And I can say, this is what I've been doing this since chapter 2, so that's good. Summation forces x equals 0. Summation forces y equals 0. And if I need it, the summation of moments about any point on this truss also have to equal 0. So in the x direction, I have RAX. I don't have any other x directional forces on this truss. So that means that that has to equal 0. That means that RAX, there is no value for RAX, or it's a 0. So in the y direction, I have RAY drawn in a positive sense, and I have 36 kips acting at D, 36 kips acting at F. Both of those are negative because they're down. And then I have plus RH in the y direction equals 0. So I can say that RAY plus RHY equals, if I bring these over, they become positive. So it's 36 plus 36 on the right-hand side of the equation, right, which is 72 kips. Right, now, since I have two equations, or one equation and two unknowns, I don't have enough equations to solve for that, do I? So that means I'm going to have to go to the moments.
In other words, you'd have to determine the moment of one of the reaction forces and then just
Perfect.
solve for the one that is unknown.
Yep, you got it. So let's go ahead and solve moments about A, okay, because that'll eliminate, if we had an RAX, which we don't, but it would eliminate both. But that's going to eliminate RAY from our equation. So here we have our 36 kip pound acting vertically. So I need, in order to find the moment, I need the horizontal distance. Well, it tells me that each of these panels is 10 feet. So that means the distance, the horizontal distance from A to B is 10 feet. So I have 36 kips acting at 10 plus 10, or 20 feet from point A. And that's going to try to spin it clockwise, which is negative. Then here at F, I have another 36, which is acting 30 feet. And then finally, I have RHY, which is going to try to go counterclockwise, so it's positive. And that's at a distance of 40 feet. And those three things summed together equal 0. So that means from this equation, I can solve for my RHY. So it's 36 times 20 plus 36 times 30, which is 36 times 50, divided by 40, right?
Oh, okay.
You see?
So,
yeah.
how do you determine the clockwise? Does it have to be like your intuition, so when you imagine?
Yes.
So how is it going to be?
Yep, you put a pin here in your mind, and then push this way, and you're going to need a clockwise spin. Clockwise spin.
Oh, because
and
if it's going
counterclockwise.
straight vertically down, it goes through E, as we can see. So then it comes at A, it goes up, so it has to be a clock.
Yep, you got it. You got it. It's exactly
like
right.
Here at RHY, it goes this way, so it would be then counterclockwise.
Yep, that's right.
I see.
You've got it. Very, very good. All right. So if I take 36 and multiply it by 50, 20, 30 is 50, that's 1,800. And if I divide that number by 40, I get 45. So the reaction RHY turns out to be 45 kilopounds. And then if I go back here, I can then say RAY equals 72 kips minus RHY, which is 45. And so that value is 27 pounds, kips, excuse me. Right? So this equals 27 kips. All right. Now, if I'm going to find the reactions here and here, the first thing I have to do is using the method of joints, I'm going to sort of, this one's equal to 0, that one's 27. I'm going to look at joint A first, and then I'll look at joint B, and then I'll look at either C or I'll look at C. So the first thing I'm going to do is look at joint A. What's going into joint A? Well, we have the reaction at A in the y direction, which is 27 kilopounds up. And then we look at the structural members AC and AB as being forces as well. Now, how do I determine the directions on these? If you think about it, look at these three forces going into point A. If this is going up and this is purely horizontal, this is going to have to be down, isn't it? Because everything has to sum to 0. So AC is going to have to go down, which means it also goes to the right. Since this is the only horizontal part to combat that, it's going to have to go to the left. So now when I do a method of joints, I can't use the moment equation in the joint because everything, all the moments going into the joint would produce, all the forces going into the joint would produce a moment of 0. So all I can do is summation forces X equals 0, summation forces Y equals 0. All right. Now in the X direction, I have minus AB, then I'm going to have plus the X component of AC. Those two things added together equal 0. And in the Y direction, I have RAY, the whole thing, minus AC in the Y direction equals 0. So like I said earlier, when I look at those two, I can use the geometry of the truss to find the geometry of these forces. And this is the only one that really has any requirement of geometry here. In other words, AC, I'm told that this is 7.5 feet, and this is 10 feet.
Theorem of Pythagorean?
Yes, exactly, right, because A to C is the vertical distance is 7.5 feet, and the horizontal distance is 10 feet. So what that means is that in the X direction, well, we can just find this angle. There's other ways to do it, but let's just say theta. This angle is going to be, I have the opposite and the adjacent, so it's going to be the inverse tangent, yes, of 7.5 over 10.
Oh, so we don't have to...
That's right. So we can make it a little bit easier on ourselves. So I go second tangent, parentheses, 7.5 divided by 10 is just 0.75. So that angle is, theta is 36.87 degrees. All right. So then I can use that. So I can say then minus the force in AB plus the force in AC, but I only want the X component. So if this angle is 36, that would be times the cosine of 36.87 degrees equals 0. And here I actually know the value of RAY, which is 27 kips, minus AC, now in the Y direction, it's going to be times the sine of 36.87 degrees equals 0. So what that means is from my Y equation, I can solve directly for the force in AC. So 27 then divided by the sine of 36.87 degrees is equal to AC. So I can take the sine of that. And the reciprocal, multiply that by 27. So I find that the force in AC is 45 kips.
Could you pull that up?
Oh, sure. So sorry. Is that better?
Yeah. So,
Let me get all that on there.
Oh, so you did them for the Y?
I did. Yeah.
Summation of forces.
Just because that's where it came out of the equation quickest. I only had one unknown here. I still have two unknowns in my X equation.
Question.
Yes.
So then, because it's in X direction, that's why it's sine.
Exactly.
That way. So then it would be totally opposed over
Yes.
hypotenuse.
Perfect. Very, very good. All right. So once I find AC, then I can plug it into this, and I can say minus AB plus AC, which I now know would be 45 kips, times the cosine of 36.87 degrees equals 0. So 45 times the cosine of 36.87 degrees equals AB, and then I can solve directly for AB. All right, so if I take the cosine of 36.87 degrees, I get that, I multiply it by 45, and I get that value is 36 kips. Okay? All right, so what that means is the only other thing I need to decide is if these are in tension or in compression. And in order to do that, so in other words, okay, let me write this. AB then equals 36 kips, and AC equals 45 kips. But are they in tension or compression? Okay, go back to our original picture. We're thinking about it from the point of view of the connector of point A. Is force AC pulling on point A or pushing on point A?
Pulling.
It is, and pulling means tension.
Pulling means tension.
So that means tension. What about AB? Is it pulling on A or pushing on A?
It's going to push.
It's gonna
going
push.
towards the connector, so we'll-
Perfect. And so those are our first two answers. All right. And so this is how we do the method of joints. Now, I'm going to finish the rest of this later because I actually have a student coming to my office and I don't want to keep him waiting. But basically, what we would do next, now we know AB, and so we can go to joint B, and we know AB, and we also know that it's pushing on the joint. So that means going into joint B, AB is going to push on joint B. It pushed on joint A, and it's pushing on joint B. So it kind of looks like, from a statics point of view, that it has switched direction. But here we are for BD. If this is pushing on the joint, BD is going to have to be the reverse of it, isn't it? So, and BC, there's nothing to match its vertical component, so BC is equal to 0. But look at this horizontally. The magnitude of AB and the magnitude of BD have to be the same because they're the only thing in the y direction. So summation forces y equals 0, AB minus BD equals 0. That means AB, which we determined was 36 kips, equals BD. So that's equal to 36 kips. And we go back to our picture, pushing on the joint. So it's also in compression. Right. So this is a complicated discussion, and we're going to finish it next time. We're not going to leave it here and turn you guys loose to the wolves. But on our next lecture, we'll pick right up here, and we'll finish going through the analysis of truss. And then also on Wednesday, we will, on lecture 26, I should say, we'll make sure to answer any questions that you have. But I'll put up a couple of homework problems just to get us started. And these do tend to be quite lengthy. So for section 6.1, I'll only put up probably 2 homework problems. So, all right. Thank you so much, and we'll see you Wednesday.